All right, here we go. Exponential growth, which is something you guys have talked about and used since like Algebra 1. But we're going to do something exciting today. We're going to derive it. In fact, we've used it quite a bit this year just as a function that you guys need to understand. So, all right. So, exponential growth, y equals y naught e to the kt is that general equation that you guys have studied. This is the final amount or population. This is the initial amount or population. This is the growth rate, k, and this is the time that has passed since the initial population. So you guys should be familiar with that. The graph of this looks like something like that. It has a horizontal asymptote, y equals 0. It goes through 0, 1. And yeah, it's kind of basic shape that we know. Now, here's a big question. Since Algebra 1, and even this year when I reviewed it, where does this equation come from? Most likely you've not derived it. So guess what? The definition of it is often described with these words. It's a population or amount of something that grows. If it grows, it grows exponentially when its growth is, and is usually equals, proportional to its current population. Proportional means, is always times the same number. And what we could do is if we interpret this, we could write this as a differential equation because growth is a derivative, right? So growth is a derivative. So they'd be like dy dt if we're using time equals k times the current population is y. The growth is dy dt. And so dy dt equals ky. And k is a constant. And with proportional, when things grow proportionally, we often use k, and that's called the constant of proportionality. But what we have here is we've taken this very common description of exponential growth and interpreted it as a derivative, as a differential equation. And up until this last week, we didn't really know how to solve these, undo these derivatives. But now we know how to separate the variables. So we bring the y to the left-hand side by dividing it. I would leave the k on the right side and bring the dt over there, which is often dx. And we've separated the variables. We can integrate both sides. And compared to some of the ones we've done, this one's not too bad. Natural log of the absolute value of y equals kt. K is just a constant, a number. So its antiderivative is going to be that number times t plus c, of course. Don't forget the plus c. And then we would exponentiate both sides to get rid of the natural logs. We're trying to get y by itself. We get absolute value of y equals. Now, rules of exponents. I've shown you guys this trick several times recently. Would let you break that up. And I'm just going to call that c. That e to the c, I'll just call c. And if we had an initial condition, I'd find the c like right away. And we probably will think of it this time. Get rid of the absolute values as plus or minus ce to the kt. Now, we're going to just go with the positive here. The c, because we've waited to find the c should take care of the positive or negative correctly. Also, if you're applying this to like a population or amount of something, we shouldn't have like a negative population. But I mean, we could use exponential growth equations for sort of non-realistic type of problems like that. Now, the initial condition, which we could have used earlier, but we often use the initial population, y sub 0 is the initial population, and that is when t equals 0. Well, let's go and use that as our initial condition. That's the y value, that's the t value, and plug those in. So y equals y sub 0, and ce to the k times 0 for time. K times 0 is 0, e to the 0 is 1. So c equals y sub 0, the initial population. And so it makes sense to go ahead and write y equals y sub 0 e to the kt for our specific solution. And what we just did was we just derived the exponential growth equation that you've been using since Algebra 1. So congratulations, you've done it. Now, while we can use this kind of, equation to measure growth, in reality, will populations just grow bigger and bigger and bigger and bigger. And so the answer is usually naturally no. There's going to be some limit to how many organisms can live in a certain area. And in fact, right now, we're dealing with coronavirus, which is a really good problem to use this kind of growth on. And in fact, in the news, I keep hearing this talk about things that are related to this, but really a more realistic type of growth is called logistic growth, which is a BC topic. You guys don't need to know it for AB. It's a BC topic, but you've probably heard about it in other classes. I don't know, bio. And so the idea is that it has a horizontal asymptote, y equals 0 on the t-axis for time. And at first, it does grow exponentially. It does look very much like an exponential curve. When the population's small, it's going to not feel the restrictions of the amount of area, the amount of food, whatever it is that needs to support a growing population. And in fact, even in a disease, there's not a lot of infected people, so it spreads more quickly to the uninfected people. But as there's more infected people, then there's less people for it to spread to. So the growth actually starts to slow down, and it goes towards what we call the carrying capacity, which is a term I think you guys have seen in other classes. And in Calc BC, we use capital M for the carrying capacity. So what happens is it approaches this limit. It levels out. Now, it technically keeps going up, but the growth does approach like zero growth. And in sort of like the coronavirus idea, that would be like 100% of the population or 100% of sort of like a region gets the coronavirus. Well, it can't spread to anyone else. And as soon as half the population has it, which happens at half the carrying capacity, it starts to slow down in how many new cases you get every day. So this is actually where the slope is the steepest. This is the max growth rate. And this is when dy dt is its maximum value. The slope is the maximum value. And where this happens is an inflection point. So in the news, I keep hearing like regular people, news people talk about when we reach that inflection point, with the coronavirus. So I'm impressed that we're talking about calculus right now in the news. They talk about flattening the curve and all these different things. So anyways, the equation for it And this is all just kind of some extra information. When you take Calc 2 next year, BC, you'll get to do this for real. It has an exponential part of it. At first, it grows exponentially. So it has that KY, has that exponential part to it. But then it has this other part that as the y value gets bigger, it makes dy dt get smaller and go to 0. So what it is, it's the carrying capacity minus y. So this is the limiting part. And so what happens is as y approaches the carrying capacity, as our population reaches its max possible, then m minus y is approaching 0, which makes our growth approach 0, or dy dt approaches 0, and it flattens out like over here. Now, in reality, people would start getting better, and so the curve would start to come down, kind of look a little more like a bell curve, which maybe you've been seeing in the news with the coronavirus. And then, hopefully people who've had it, who've gotten better from it, won't get it again. I think most of the graphs I've been seeing actually are numbers of new cases. So when the curve starts to come down, more people are getting it. So they're kind of considering more people total are sick than before. But now the new amounts per day are getting smaller and smaller. So we've passed that inflection point. Anyways, this is the growth. This is the differential equation for logistic growth, and we will get to. You guys can't solve this one. It involves some integration techniques that you won't learn until next year, also. And logistic growth is on the Calc BC test. For you guys, it's just exponential. On the back here, I just have not an exponential growth problem, but one more differential equation, because there's usually a lot of questions about it on AP tests, and it's something that we've learned this technique of separating the variables just this week. So this is just one more example. Now, just to kind of practice several of the things that we've been doing, could we sketch the slope field? And if you want, you could pause the video and try and sketch yours. And I'll sketch mine, and you can see if you got it. You should be getting pretty good at this. I mean, if anything, it's pretty straightforward. It could be tedious. Hopefully you look for patterns. So I'm going to go ahead and start writing. So when does it equal 0? Well, that would be when y equals 0, which is the x-axis. And so that's going to be, this is the x-axis, this is the y-axis. So 0, 0, 0, 0, 0, 0, 0. And I just took care of 1/7 of all those points. When is it undefined? And that would be when x minus 2 equals 0, which is when x equals 2, which is a vertical line right here. X equals 2. Now, technically, we shouldn't draw vertical tangents because they technically don't exist because they're undefined. And really, that might not even be the issue. We might have a corner or cusp, and that's why it's undefined. But we'll see in a second. So let's see if we can find some other patterns. There's probably some symmetry, here, and if you kind of confirm that, then that could speed things up. 1, 1 would be 1 over -1, which is -1. 3, 1 would be 1 over +1, which is +1. So we're starting to see that. I bet this one, if you do 1, -1, that's going to be +1, and this one's going to be -1. So you start to see this sort of radiating slopes. Now, 0, 2, 0 for x, 2 for y, be -1. Oh, but this is -1. And so you start to see these lines going. And so 1, 2, that would be 2 over negative 1 is negative 2. I bet this one is also negative 2, and I bet this one is positive 2, and this one's positive 2. And if we do 1, 3, that's 3 over negative 1 would be negative 3. And so this one's probably negative 3. This one's probably positive 3. This one's positive 3. Interesting thing is all the slopes are pointing right to this dot. So I bet this one was down 1 over 2, 1/2. Let's plug it in. 0, 1. 0 for x, 1 for y is negative 1/2, in fact. And this one's positive 1/2, and this one's probably down 1 over 3, and this one's probably up 1 over 3, and this one's probably up 2 over 3, and this one's probably down 2 over 3. Anyways, I think that's good enough. So, kind of interesting graph. It's all kind of seems to be exploding from there now. This is the initial condition. So we could talk about what would that look like if we graph that here. So 3, negative 1 is right here. And so a lot of times this is what you're asked to do either after you sketch your own slope field or they give you one that's already sketched and they say, sketch the particular solution for this initial condition. So what you usually do is you follow this. Now, one of the things I've told you is that once you get on, if all these slopes are all pointing to each other, then you're stuck on that. It's like an asymptote of some type. This isn't quite like that. I mean, we could do that, but we'll come back to this and we'll see what happens. So let's see if we can go ahead and solve the differential equation. So I'm just going to rewrite it. We're going to separate the variables. So the y needs to come over the left-hand side, and the dx comes over to the right-hand side. The x minus 2 is still in the denominator. So we separate the variables, integrate both sides. This is natural log of absolute value of y. This is natural log of the absolute value of x minus 2 plus c. Now, if you're uncomfortable with that, we could do a little u substitution. U equals x minus 2, du equals 1 dx, which means if we rewrite this, it's going to be du over u, which is natural log of the absolute value of u, and then you replace u with x minus 2, and that's what we got. So this is an inner function, but chain rule derivative of it's going to be 1, so maybe that's easy enough to not do all that as short. Let's find the c value now. I just feel like that's going to be the easiest. So we're going to plug in 1 for the y value and 3 for the x value. And we get natural log of 1, which is 0. We get natural log of 1, which is 0. So c equals 0. Okay, that's nice. So let's rewrite it. Natural log of the absolute value of y equals natural log of the absolute value of x minus 2. And don't have plus c. Got to get y by itself. Exponentiate both sides. And then, so we have absolute value of y equals absolute value of x minus 2. Now I'm going to get rid of the absolute values around the y, plus or minus. I'm not getting rid of the absolute values around the x minus 2. I can't really do that right now. Now I should choose plus or minus, because if I leave plus or minus, that's 2 answers. I'm trying to find one specific answer. So if we plug the initial condition in, 3 in for x, and we should get positive 1 out, so we're going to go with the positive. So this is what we have right now. Now remember, we got to deal with the domain. And one thing I mentioned, I think, in the last lesson is any answer you get by solving a differential equation, any answer that has absolute values in it, you're going to be able to write without absolute values by the time you figure out the domain. Because the absolute values for any kind of function, you should create some really sharp corners on your graph, which are places where the graph is indifferentiable, the derivative is undefined. And that's one of the places you're supposed to break up your domain for the solution of a differential equation. Now this right here, its domain, it's all reals. You can plug anything into that, but we also need, so we check that, but we also need to check the original derivative. And people just forget to do this, but you have to for these problems. And so is there any places, any x or y values that cause that to be undefined? Imaginary, division by zero, even roots of negatives, natural logs of negatives or zero, all those situations. And we have a problem. X minus 2 cannot be 0. X cannot be 2 because it creates division by 0. Now, what I would usually do next is I'd do a little number line. I put an open dot there. Any problems here, I'm going to just represent with open dots. I don't have to think as hard to actually find this domain like I would normally, because I know that at any point where we get an issue, a discontinuity or indifferentiable point, we're going to break it up there. And it's going to be a single open interval, one open meaning it's never going to be solid. And it depends on where the initial conditions. Initial conditions at x equals 3. So that's your domain. So the answer would be, for 2 to infinity. Now, look at the picture. What does this graph look like anyways? This graph right here is an absolute value graph, a linear absolute value. And those are like V-shaped graphs that you guys learn how to graph in Algebra 1. And the minus 2 on the inside shifts it to the right 2 units. And so this would be that graph right here. This and this, it'd be this V graph. And so the reason that these are undefined right here isn't because they're vertical. It's because you're getting a corner. That's why the derivative is undefined. Now, the domain is supposed to be a single open interval. And what we're doing is we're breaking it up right here. So this has to be an open dot. You got to make sure it looks open. We're not going to include that part. This is it. So if they ask you to sketch the particular solution on a slope field, it's just going to be this. It needs to be an open dot, this way, arrow, don't include the other part. But that also means that since this is our domain, x is always going to be bigger than 2, which means the inside of this is always going to be positive. Our best final answer would just be y equals x minus 2 for that domain. And that's the best answer. That's the answer I'm looking for if you want to give full credit. That's the nicest answer. So anyways, there's one more differential equation. Assignment today be worksheet 11.4. And it's some free response problems with slope fields and differential equations. Okay. So that's it. Do it. There's links in the video for any of the worksheets